welcome to Enough with the Science. And basically what we're doing here is we're talking about science. And Senan is a bit of a science nut, and I'm not. So he understands things that maybe most people shouldn't. And he tries to explain them, and I ask him questions to try and put him off, essentially.
And Joe challenges me to put everything into words of one syllable.
Even I can understand them sometimes. So this is actually part two. This is our first part two of a two-parter, obviously.
Yeah. So last week we gave an introduction to the electromagnetic spectrum, or electromagnetic radiation, or light, as a lot of people call it. And this week we're going to continue on that theme and finish off that whole electromagnetic spectrum stuff.
Finish off the electromagnetic spectrum.
Yeah, absolutely. We've had enough of it.
Well, yeah, after two episodes.
The universe will just have to limp along on its own without it.
I imagine listeners might have had enough after the first episode, but we shall see. That remains to be seen.
Let's just do a quick recap of what we spoke about last week.
Okay, don't ask me any questions.
Yeah. So anyway, we found out that electromagnetic radiation, it's all radio waves, light, X-rays, gamma rays. It's all made of the same stuff. It's all EM radiation. And this EM radiation is emitted when charged particles change speed or when they change direction. That's how
this is coming back to me. Yes.
That's how it's born.
Okay.
And one of the weird bits, of course, is that it's not one wave like we see when you look at the beach. It's two waves together at right angles to each other. You've got an electrical wave and a magnetic wave travelling together. Did you recall that bit?
No. Well, there was something about a cross. I remember there was a cross.
Yeah.
And yes,
that was the
flown
cross
through the
thing.
universe.
Yeah. Now we really delve into the weirdness. We discovered that it is both a wave and a particle at the same time.
Oh, yeah. I remember this now. This is where it started to hurt.
So the particle is called a photon. You'll be hearing a lot about photons today. And it's really one of the most difficult aspects of electromagnetic radiation to understand, is the fact that it behaves both as a wave and as a particle at the same time. And that has been proven with different scientific experiments.
Maybe the experiments are wrong. Maybe there should be a third thing. Maybe it's not a wave or a particle. It's something else, a warticle.
Yeah.
Or a pave.
You know, you could well have come up with the perfect encapsulated description of it there.
A warticle park.
Moving quickly along before we're kicked out of the Academy of Science.
Again.
There's a couple of interesting measurements about EM radiation. I'm going to call it EM radiation from now on, because calling it electromagnetic radiation is sooner.
I bet you don't. I bet you say it. I bet you say electromagnetic radiation again at some point.
I'll do my best.
EMR.
Anyway, so there's a couple of measurements that are important. Frequency is one. That is how many waves every second. So if you were standing still and you were watching the waves going past you and you counted them, it's how many of them pass you in a second. That's how frequent the waves are, or the frequency. And the other important measurement is wavelength, which is the length of one wave from a peak to a trough, or a trough to a trough. Now, just one important point to note about that. The higher the frequency of the wave, the more energy is in each photon. And that's the difference between all these different kinds of radiation, be they radio waves, light waves, X-rays, gamma rays, etc. It's the amount of energy that the photons carry, and the frequency, which the two things are related. The higher frequency, the more energy.
So the more waves that pass a certain point per second, the higher the energy.
Correct. The photons that are part of that system have higher energy, So each photon is kind of like a discrete packet of energy. So you can't kind of have a half a photon. You either have the full photon or no photon at all.
But the photon is part of the wave.
Oh, we're not going back over this
Well,
again.
Can we not just, I give up. Okay, there's photons in the waves as part of the waves, and they are the waves, and they're all the same thing.
Yeah, that's it. Yeah,
there we go.
That's it.
Okay, so all of this EMR, see what I did there? EMR.
EMR.
Yeah, there you go.
Yes.
Let's save energy.
Let's do that, The podcast will be over in about 10 minutes if we keep abbreviating it down to
electromagnetic radiation. So all of this electromagnetic radiation is flowing in all directions at the same time.
What do you mean by that now?
Well, so it's not like we established last week. It's not like a wave on the sea that's flowing one way, just on one plane. It's on all the planes.
So you're talking about if there's like a light bulb turned on.
Oh, yeah.
And light appears to go in every direction from it.
Yeah.
So there's waves going away from it in every direction. It's a bit like if you It's a three-dimensional version of what happens in the sea, which is kind of two dimensions. If you throw a big stone into the sea, and suddenly you see waves spreading out in circles away from where the stone went into the water. So it's a bit like that. The waves are spreading out in all directions, but they're kind of, you can think of them as individual waves going, one going left, one going right, etc. One going up, one going down.
And these are everywhere.
Well, they, like, we can see anywhere you can see light. There's light waves traveling around.
Okay. But like, even like as we said last week, in deep space, there's
Oh yeah,
all of the.
There is certainly microwave radiation and infrared radiation and light all over the place in space. Yeah. And all of it, of course, has a speed limit. And
someone always wants to break up the fun, don't they? He wants to stop. You're going too fast. Slow down.
Well, unlike the speed limits that are on the signposts at the side of the road here, you can't actually go any faster than this speed limit. Nobody can. Nothing can. So it's not like a suggestion that we
This
have
is
in
the limit
local laws.
of.
This is the universal limit.
This is like actually like it is the limit of speed itself.
Yeah,
It's not just a speed limit. It's the speed limit.
It is the speed limit of everything.
It's the limit of speed.
Yeah, and it's a huge number. It's slightly above 1 billion kilometers per hour. Now, I don't know about you, but I can't visualize in my head what 1 billion kilometers an hour are. So let's take that down to something that's a little bit more understandable. 300,000 kilometers per second. Does that help you?
No.
Okay. Right. We're going to go even lower.
Yeah.
7 times around the Earth in 1 second.
Okay.
That's how fast
Superman speed.
light can travel in a vacuum. Now, so light traveling through water, for example, travels at a slightly different, slower speed. But light in a vacuum is the actual speed of light, and it's 7 times around the Earth in 1 second. And it's the ultimate speed limit for everything. And why is that? It's baked into Einstein's theory of special relativity, which he developed
here we go.
about 100 years ago.
Is it big words again now? Monosyllables, we said.
So Einstein came up with these two theories, general relativity and special relativity, and they have held true despite, 100 years later and a lot more sophisticated, experiments being done by scientists and a lot more sophisticated calculations on computers and so on. And still Einstein's theories hold up. It's incredible. The mathematics that he did back then is still fundamentally correct as far as we know.
So no experiments have contradicted his
Not
theory.
in any substantial way. There might be little threads being pulled at the edges here and there, but not the substantial, underlying stuff is still correct.
Brainy lad he was.
Unbelievable.
Yeah.
They broke the mold when they made him. Anyway, so his theory of special relativity tells us that the mathematics that he developed tells us that as something with mass gets faster. So what do you mean by something with mass? Well, you can think of it as something that's heavy. So mass and weight are not exactly the same thing, but here on Earth where there's gravity, we can treat them as if they're the same thing. So if you pick up something that you can feel weight in your hand, that's the mass of it that you're feeling. So his theory says that if something that has mass speeds up, its relativistic mass increases. What does that mean? It means that it doesn't actually get heavier, but it behaves as if it's getting heavier, right? So,
and there's a difference.
Who knows?
There's a difference. So if you weigh it, it behaves like it's heavier.
Yeah.
So it is heavier.
Yeah, look, I think for ordinary mortals like us, it means the same thing.
Okay, I think we can just accept that. Like, it would be, we don't have the instruments to separate behavior from actuality.
Anyway, one of the implications of that of it as it speeds up, of it appearing to get heavier, is that you need more and more energy to make it go faster. You need a heavier thing needs to be pushed harder than a light thing to speed it up, right?
Okay.
So this thing is behaving like it's getting heavier and heavier the faster it goes. So you need more and more and more and more energy to make it go faster and faster. And if you follow Einstein's equations, you come to a point where it says to increase its speed to the speed of light would require infinite energy, which is a nonsense. There's no such thing as infinite energy. So what it means is that nothing that has mass can be accelerated to the speed of light.
And so speed of light is the limit. There's obviously several points before that where it becomes almost impossible, awfully difficult.
Awfully hard.
Yeah.
Awfully
incredibly
hard to do it. Yeah. Now we're talking about, so these are massive speeds. So anything that we have accelerated as humans is crawling slower than a snail. We're not getting into that. This problem about needing more and more energy to push things faster doesn't affect us because we haven't made anything go fast enough.
What about those things that are shooting around the tube in CERN? They're pretty quick, aren't they?
Yeah, they're pretty quick, but they're, of course, they've tiny amounts of mass.
Yes.
So the amount of energy required to accelerate them is relatively small, but still, the faster they make them go, the more energy they need to make them accelerate. Yeah. So, however, now let's talk about why does light travel at the speed of light, or EM radiation really travel at the speed of light, and it's because the photons have no mass. They have no weight. The photons that light is made from have no mass. They're effectively, if something has no mass but exists, it's pure energy. So they are packets of pure energy, and they are born traveling at the speed of light. They don't accelerate from 0 to the speed of light. They are born traveling at the speed of light, and they never come below that speed.
Until they die?
Until, well, if for example, your eye sees light coming from a light bulb, the photons that have gone into your eye have reacted with the cells in your eye and been absorbed. That's how you got to see that light.
Okay, so they're gone. They're not passing through you.
Oh, no, they're gone. Now, if they were X-rays, they'd be passing through you,
okay.
all right.
Obviously.
No, but the light doesn't. So yeah, it's all a consequence of the mathematics that Einstein worked out, that we know all this stuff. And I mean,
so if you turn on a light, right?
Yeah.
And you're 300,000 miles away.
Yeah.
Kilometers away.
Yeah.
You would see the light in 1 second.
Yes.
If the light was strong enough.
Yeah.
But there would still be photons even if you couldn't pick it up, probably.
I mean, if you had a sensitive, some photons would reach there, but if you had a sensitive enough detector, assuming nothing got in the way to stop them in the meantime.
Yeah.
So the sun, right, is 8 light minutes away from Earth.
Mm-hmm.
So if the sun was to suddenly get extinguished, we wouldn't find out for 8 minutes. It would look exactly the same until all the old light from before it got extinguished had passed us by.
So, as part of a philosophical discussion, we can only see the past.
Correct. Yeah. Even the fact that you and I are sitting a metre apart, what I'm seeing of you is the past.
Yeah.
You could be dead. You could be dead now for all I know.
Yeah, I could be milliseconds ago. I could have just had enough of this and just thrown myself against something sharp.
No, it's not that bad. Use something blunt. It'll be easier. Anyway, so here's an interesting conundrum for you. So you're driving down the motorway at night time in your car. You're doing 700 miles an hour. And
as usual,
you push the button on the dashboard to switch on the lights. So the light that's leaving your car at the front, you would imagine, is travelling at the speed of light plus the 700 miles that you were doing already. That's what you would intuitively think is happening.
Mm-hmm.
That's not happening because it's stuck at the speed of light. So what actually happens is that time is slowing down slightly for you because you're travelling, because you're moving. And that means that the speed of light, the combination of the speed of your vehicle and the speed of light being emanated, still doesn't exceed the actual speed limit. So the faster you travel, the more time slows down for you. And that's another one of those really mind-bending things.
See, we should do a whole episode just on that. That alone is just big enough. The faster you travel, the slower time goes.
Yeah. And do you know one of the most commonplace thing we use every day that's affected by that is GPS. So GPS satellites are traveling quite quickly. I mean, they're not traveling at 300,000 kilometers a second, but they're traveling quite quickly, several thousand kilometers an hour. And GPS accuracy relies on extremely accurate atomic clocks that are in those satellites.
Right.
And so the satellites are transmitting a time code, and that's how your phone figures out where you are. That's how it works out position. But they discovered after they set up the GPS system that it was inaccurate. And the reason it was inaccurate was because the time on the satellites was moving slower than the time here on Earth, because they're moving faster than us.
Right.
So they're going fast enough for us to see the effect. So they have to literally manually tweak the clocks on the GPS satellites to run slightly fast to compensate for the fact that time on those satellites is running slowly.
So even on a plane?
Yeah, now the speed a plane is traveling at, it's very, the difference is tiny. But there has been an experiment done where 2 atomic clocks that were synchronized to the exact time. One of them was put on a plane, flown around the world a couple of times, and then they took it off the plane, and sure enough, it had slowed down.
Yeah, right.
Ooh. So yeah, it's mind-bending stuff.
So if you want time to speed up, we just have to stay still.
Yeah, I mean, there's a well-known trope in science fiction novels that a character, maybe their long lost love is going to be years before they'll come back to see them again, and they don't want to be an old person when that long lost love comes back, so they go into a spaceship and start traveling around really, really fast to slow down their aging, so that when their lover comes back they won't be too old.
Oh my God, I hadn't even thought of that. So like if you're on a really, really fast spaceship, your aging process slows down.
Yep. So
this is why they're investing millions in private space companies. I can see it now. I can see they weren't doing it for the good of mankind.
Let's say we were able to build a spaceship that was able to go at 30-40% of the speed of light, and we sent it off to some star that's 20 light years away or something, so that astronauts could explore that star, and then they come back again in the same spaceship, so that's 20 light years each way. By the time they get back, the people that they knew on Earth would be a lot older than they expect them to be. Some of them might even be dead from old age.
Yeah.
It's a weird thing.
Yeah, I've seen a couple of movies. Interstellar melted my head when they were trying to explain that whole concept. People being in different places.
Yeah. My favorite line in that movie: "Those aren't mountains." Do you remember that?
No.
They landed on some water planet.
Yeah. Oh, there were waves.
There were massive tidal waves. Yeah.
Yes. Yeah, it's coming back to me.
Anyway, back to the script.
Oh yes, back to the EMR.
We're going to tour through the various types of EM
the locale
radiation.
here on the left.
So we're going to start at the low energy end, and that's of course radio waves.
No reflection on this podcast.
No, well, this is the modern world, and it's all going to be in ones and zeros on the internet.
We're still wireless. It is still wireless production.
So we're talking about long wavelengths here. So anything from millimeters up to kilometers. In fact, some radio waves are kilometers in length. FM radio that people listen to music on, wavelength there is about 3 meters. AM radio, which is an older fashioned and I think is used mainly for talk radio in the US, and it's not hardly used here in this part of the world anymore. Wavelength there is about 100 meters.
And does that mean that if you wanted to broadcast to further away, it would be better to use AM?
Yeah, but not probably for the reason you're thinking of.
Okay. I'm right. Just let me be right. You don't have to correct.
You are
right.
Okay. Yes. You're right. I'm not going to question your thought process.
Just let
you're
me,
right.
Yeah. Don't explain me how I'm wrong.
So it's an interesting point. Longer wavelengths are able to diffract or bend around obstacles, and they're also able to bounce off the ionosphere, which is a layer high in the atmosphere. So that's why some of those, like if you consider a lot of EM radiation is pure line of sight. So for example, if I shine a torch, there's a shadow caused by something in the way of the torch because the light is going in straight lines and it doesn't go around the back of where the shadow is, if you know what I mean.
Yeah.
That means that using radio waves for communications, if you don't have line of sight, so you're trying to communicate with somebody who is halfway, say a quarter of the way around the planet, so the curvature of the Earth is in the way. You can't actually fly a straight line to them. You'd have to go through the Earth to get to them. So these long wavelength radio waves, they can bounce off the ionosphere and effectively bounce around the curvature of the Earth and go much longer distances.
Okay.
So that's kind of why it's handy.
And
for
all those movies from the 1970s where everybody seemed to have like a Trans Am car and a radio, like kind of a CB thing.
Yeah.
Were they AM?
I don't know. I think the CBs in this part of the world were FM band, but I can't remember. There was friends of mine who experimented with that stuff.
The Breaker 19.
All that.
There's a bear in the hardware.
All that malarkey and movies with
Smokey and the Bandit.
Yeah, that's the one. Yeah, that's the one. So another reason that radio waves are good for communication is they penetrate through walls and wood and stuff easily, and that's because the energy in the photons that these long wavelengths have is low energy, and it's too low to interact with the atoms in the walls. So higher energy photons would be at the right level of energy to actually be absorbed, for example, by the walls or the timber or whatever. Yeah. So that's another reason why radio is good. So obviously there's AM, FM radio, there's television signals, Wi-Fi, Bluetooth, GPS, radar for finding planes and ships in the distance. All of that is using radio waves. Now, there's an interesting question. How do we make those radio waves carry our voice?
And the information in them.
Yeah.
I asked them nicely. Send them a strongly worded letter.
So the audio that's coming out of my mouth right now is setting up waves in the air. We can't see them, but there are compression waves in the air being caused by my voice. And so there's a particular pattern of waves traveling through the air. So we can take that pattern and superimpose it onto the radio waves. So that's essentially how we're making the radio waves carry the information for us. It's a process known as modulation. So what you're just doing is taking the pattern of my speech and superimposing it onto, like, modifying the radio waves to take that pattern.
It's not only speech, like it's everything that
data
is audible.
Oh yeah, or everything that's audible, but also even ones and zeros of data. We can modulate that. And there's kind of two main schemes for doing that. One is called amplitude modulation, which is AM radio that we mentioned earlier on. So what that does is it varies the height of the waves a little bit. That's how it imposes the pattern, by making small changes to the height. And the other kind, FM radio frequency modulation, it changes the frequency of the waves continuously, just by slight amounts. Yeah. So that's how the pattern gets encoded onto the radio waves. It's interesting stuff.
It just blows my mind that Marconi wasn't like.
Yeah, that he figured out all this stuff.
Like, was it? But did he figure that out, or was it sort of a practical thing? He kind of went, okay, I connect up these two things, and you can hear it over there, and then okay, then we make a bigger cable, and we move that over here, and suddenly or was he actually sitting down going, yes, I think I'll change the amplitude. Yeah. Here and the frequency of these particular waves.
Yeah, I wonder how much he understood about it. I don't know. Yeah. So what happens?
That's another show. I'm writing that down.
How does the receiving radio at the other end pick up the signals? So it's got an antenna, and the waves passing by that antenna make the electrons that are in the metal of the antenna wiggle up and down to match the movement of the radio waves as they pass by the antenna. And then there's an amplifier, so that creates a wiggling current, if you like, in the antenna, and there's an amplifier in the radio receiver that picks up that tiny current and amplifies it, makes it bigger until we can hear it.
And that picks it up at a specific frequency.
Yeah, it's able to. The electronics are able to tune into the correct frequency. Yeah. But also there's different frequencies use antennas that are of slightly different length. So the antenna has to be a multiple of the wavelength, is it the wavelength or the wave height? You have me there now. I can't remember. But anyway, the point is,
you failed. Sorry. Next.
The point is that the antenna has to be more or less matched to a set fraction of the actual wavelength or the wave height. Microwaves moving slightly up the spectrum.
Okay. So what we are basically increasing the frequency as we go, isn't it? Increasing the frequency and energy.
We're increasing the frequency and reducing the wavelength.
Okay.
So as frequency goes up, wavelength comes down. So the wavelength here in microwaves, we're in the range of from millimeters up to about 30 centimeters. So that's like from millimeters up to about 1 foot in old money. It's the perfect frequency, or at least one particular type of microwave is the perfect frequency for heating food. So that's 2.45 gigahertz. That's what your microwave oven is using. So what does that mean? 2.45 gigahertz. So 1 gigahertz is 1,000 waves per second frequency, right? So almost 2,500 waves per second is what your microwave oven is producing. And so that is energetic. The photons at that particular frequency are energetic enough to make the water molecules wiggle around violently, so that the friction in the water molecules heats them up. That's what's going on there. And but also it's got a reasonably long wavelength. It's 12 centimeters. That's long enough to penetrate deep into the food.
So all a microwave oven is doing is boiling the water inside the food.
Oh yeah, heating up the water in the food, or it might also have the same effect on fat molecules.
Okay.
But it's essentially making them wiggle violently in tune with the speed of the waves that are passing through it, and that wiggling causes friction in the food that heats up the food.
Okay. So it's not actually cooking the food; it's boiling the water, which is then cooking the food.
Yeah, pretty much. Yeah.
Wow.
Yeah.
Every day is a school day. Yeah. Every day is a school day.
Every day is a miracle, as Caravan Palace say. That's a band you probably never heard of that I like.
Yeah. Well, I've only heard of it because you like it so much.
Anyway, so
We'll get them on the show.
my believe it or not, they do all their songs in English, even though they're a French band, so they could probably out talk us as well. Microwaves are actually used also for some communication in the same way as radio waves. The reason is mainly that they carry, because of the higher frequency, they're able to carry a very great density so you can squash a lot of information into a small amount of microwaves. So they're used, for example, say you make a phone call on your mobile phone, the signal initially goes probably over FM from your phone up to a nearby antenna on top of a hill somewhere. But that antenna then has to send on the call to some other place, often 150 miles away, and it typically will have a microwave dish on the antenna sending that signal, and your call and hundreds of others that are going on at the same time, all on that one microwave band to some other place.
Okay, so like the radio waves is kind of like country road, and the microwave is like a motorway.
Pretty much, yeah. So now we don't wholesale use microwaves for all communications because we don't want to be heating up everything around us unnecessarily.
I thought that might be like, or cooking ourselves.
Yeah, well, it is used. There is microwave radar used for aircraft air traffic control. It is used for some satellite communications out in space, and some Wi-Fi bands do use microwaves, but they're very low power, so it's not enough power to actually cook us.
Thank God for that. And some people misuse them by making their coffee in them.
Yeah. And microwaves led to another fascinating discovery in astronomy, something called the cosmic microwave background.
I knew we were going to get back to space. I knew it was only a matter of time.
So this is scientists discovered that if they pointed a very sensitive microwave receiver at any place in space, any point of the sky, they could pick up these really weak microwave transmissions. Well, transmission is probably the wrong word. Microwave radiation. It was everywhere.
And somebody must have gone, aliens are cooking.
The aliens are heating up their curry. Yeah, if only that were true, and it could well be true in some places, but it's not the cause of most of it. So it's actually the oldest light in the universe. It's left over from the Big Bang. It was light that was produced 13.8 billion years ago during the Big Bang, and back then it was visible light. But the universe has been constantly expanding since the Big Bang, and that has been stretching the wavelength, and it's now microwaves. So what was once visible light, by the expansion of stretching of the fabric of the universe, which is still happening today, those wavelengths got stretched out until there were microwaves. And we see this real weak echo of the Big Bang everywhere we look.
And is it likely that if the universe keeps expanding, as long as it's going to, that they will become radio waves? No.
Oh yes, yeah. If I'm
hooray! I'm following what's going on here. Hooray! I'm delighted with myself. I'm delighted. Look at that. I think we finished there. I never get things this right.
Yeah, I tell you, your scorecard is going to be really good at the end of this episode. So yeah, it's interesting. The cosmic microwave background is like everywhere. We'll move slightly up the EM band and come to infrared, which to you and me is heat. Essentially, if there's a heater on in your room and you put your hand beside it and you can feel a warm glow on your hand, that's infrared radiation hitting your hand coming off the heater. So in terms of wavelength...
So all heat is... All heat is not infrared.
The propagation of heat through space
is infrared.
Is infrared, yeah.
So from the sun to here is infrared.
The heat element.
Yeah.
But obviously there's also light, there's ultraviolet, etc.
Yeah.
But there's another, just to briefly clarify the way you asked that question a minute ago, a heater here on Earth where there's air around you in the room where the heater is on, heat is also being transmitted using something called convection, where air around the heater is being heated up. It becomes a bit less dense than the other air that hasn't been heated up, and it rises up. And you get this current of rising air being caused, and that's another way of transferring heat. But out in space, if your stove was lit out in space, if you could find the oxygen to support the combustion, that wouldn't happen.
It's the worst analogy ever. You would light your stove in space, and you can feel the heat, even though you can't. But if you could, that would be infrared.
No, you will feel the infrared. The convection won't happen.
The convection won't happen.
Yeah. You will feel, that's the point of making. You only have the infrared then. So in terms of wavelength, we're talking about between 700 nanometers, so nanometers are really, really small, and to around 1 millimeter. So the longest wavelength of infrared is around 1 millimeter. And literally everything you have ever touched is emitting infrared radiation. Like, even you take a block of ice out of the fridge, that is, believe it or not, still emitting infrared radiation.
Liquid nitrogen.
Liquid nitrogen, yes. Anything that is warmer than absolute zero, which is I think around about minus 270 centigrade, is emitting infrared radiation. And that's happening because the property of something being hot is down to the vibration of the molecules in it. So the hotter it is, the more those molecules are vibrating. So
I think we'll use dancing from now on. Molecules are dancing. The more they dance, the hotter it gets.
Yeah. So it's actually, like we said, the thing that causes EM radiation to be born is charged particles changing direction or changing speed. So remember those molecules that are vibrating, they have electrons orbiting around them. So those electrons, which are charged particles, are going over and back, over and back, over and back. And that change of direction each time they wobble one way or the other is actually generating the infrared radiation. So yeah, it's interesting. Infrared is everywhere around us. What do we use it for? Well, astronomy, there's a huge use in astronomy because the length of, well, I should talk about, we're all familiar with visible light and the spectrum, the 7 colours of the rainbow, right?
Okay. Yes, we are.
So
I think I can speak for all our listeners.
Well, yeah. So that piece of the electromagnetic spectrum is much shorter. The piece we can see is much shorter than the infrared piece, right?
Right.
So another way of saying that is that in the infrared band, there's a lot more colours than the 7 we can see in the visible band. So if you use infrared to, a camera, a telescope that can view infrared, and you use it to explore the objects that are out in space, you'll see much richer pictures with more colours, more subtlety in them than you would with just visible light. So that's one reason why it's useful for astronomy. Another one is that there are, in many parts of space, there are dust clouds and gas clouds that visible light won't penetrate through, but infrared will penetrate through. So it effectively allows us to see through some of those obstructions and see what's behind them.
But so the infrared camera is picking up infrared, but
Yeah.
so that's essentially heat. Anything that is emitting heat.
Yeah. Well, heat is just another form of VM radiation,
Yeah.
And then, of course, in order for us to be able to see those pictures, the computers that receive that data have to downshift it into the visible spectrum.
Right. Okay.
So the pictures, like say the James Webb Telescope, which is one of the space telescopes and uses infrared, any pictures you see published from the James Webb Telescope, those have been shifted down by the computers into visible light, so we can appreciate them, because we would not be able to see them with our eyes otherwise.
And is infrared? It's like those cameras that pick up animals at nighttime.
Yeah,
That's an infrared
that's picking up the body heat emitted by the animal.
Yeah.
Thermal cameras.
A thermal camera, but is the thermal camera then shifting that down
Yes.
to be visible?
Yes, yeah. But what it's doing is, right, so remember the landscape around the animal is also emitting some heat, but what it's being very selective. It's saying heat below a certain level I'm going to treat as black, and heat above that level, i.e. the heat coming out of the animal, I'm going to treat as brightness. So it's all about how the image gets processed by the computer that allows us to see it. So your remote control, certainly the older style of remote control anyway, uses infrared. There's an infrared receiver in your TV and there's an emitter on the remote control, even though so you can't see it. But if you point your mobile phone camera at the emitter of a remote control, you'll actually see the light then. But your mobile phone camera can see some infrared.
Oh.
Yeah.
There you go. There's an experiment to do at home.
Yeah.
And I mean, for me, maybe at home for you listeners as well, but I'm going to do that later.
So what else? Weather satellites use infrared cameras because they can see through the clouds. So satellites that we have up in space that are trying to predict weather patterns, they will use a mixture of infrared and visible light because they see different things.
And I'm assuming that infrared is benign to living stuff.
Well, it depends on how much of it you receive.
I mean, if you stand in a fire, obviously.
Yeah, So if you're standing beside a very strong infrared source, it's, your skin is going to burn.
Okay.
Or you're going to burn.
Not just your skin. You.
Yeah,
Don't
yeah,
separate the
yeah,
two.
Yeah. So it's a question of everything in moderation.
But the general background infrared that you're exposed to on a regular basis.
No, nothing to worry about. So now I suppose we come to the one that we're all familiar with, which is visible light. And it's only a tiny fraction of the full electromagnetic band, the full spectrum, starting with radio waves and ending at the other end. We'll talk about later with gamma rays. Like the visible part that we see, it's less than 1% of the entire EM spectrum that our eyes can actually detect. In terms of wavelength, you're talking about between 400 to 700 nanometers. Again, very small, but smaller than the infrared we were talking about. In terms of how many waves would fit in 1 millimeter, about 2 million visible light waves would fit into a single millimeter. So they're very short wavelengths. And they carry quite a lot of information. Now, the interesting thing is, why can we see that bit? Like, any ideas?
Yeah. Well, evolution, I would imagine.
A mixture of evolution and the particular kind of light that comes out of our nearby star, which we call the sun.
Yes.
It's the peak. So different stars you look up in the night sky and you see stars all over the place, and different stars are emitting light, or EM radiation we'll call it, in different parts of the EM spectrum. But our particular star, the sun, the bulk of the light it emits is in what we call the visible part of the spectrum.
So are there stars that don't emit any visible light?
Neutron stars, I think, which are kind of the remnants of dead old stars.
Yeah.
And then there are dim red ones. I should think of the names. There's a particular name for them that
Red giants, red dwarfs.
They could be red dwarfs or red giants. I'm not sure, but they emit very little visible light. A lot of it's down the infrared range.
Right.
So yeah, there are different kinds of stars, and our star emits a certain amount of ultraviolet radiation, but other stars might emit a hell of a lot more, and so on. It's likely, or the scientists who are good at figuring out evolution think it's likely that vision first evolved underwater in creatures that were in the sea. And interestingly, visible light is able to penetrate through seawater. So that was another reason why we can see that part.
Okay, so the other, like ultraviolet and those don't?
They don't, yeah. Not very far.
Okay.
Like ultraviolet might go down into the water a centimetre or something, and then they stopped, So that's kind of why we can see it. And the reason it penetrates water is a bit like something I touched on earlier on. The energy of the photons in visible light is the wrong level to interact with water, so it just passes through. It doesn't kind of interfere with the molecules or get absorbed by the molecules of the water, up to a point. I mean, visible light does eventually peter out after about 80 or 90 meters of depth, but the shallow seas, it illuminates the shallow seas, no problem.
So I imagine if there was any sort of evolutionary advantage, either now or in the future, to being able to see ultraviolet or the other parts of the spectrum, then we will evolve to do that.
Yeah, I mean, and insects, there are some insects who can see some of the ultraviolet that we can't see. Oh. And there are patterns on the petals of some flowers that are only visible to creatures that can see ultraviolet, because those patterns are effectively reflecting ultraviolet colour rather than the visible colours that we can see.
Oh, yeah. What was that movie with the big tall blue people?
Yeah, I know the one you're talking about. Yeah, the big, and they had unobtainium in it. I remember that.
But because like when she threw his avatar, that's it. Yeah. Because he lit a fire in the nighttime. She's going, "What are you doing?" She threw the thing away, and suddenly the whole forest lit up, like without the need for visible light. So.
There you go. Something else is interesting. It has visible light has just the right amount of energy to excite certain electrons in pigment molecules, and that enables the vision in our eyes. There's pigments in the cones in our eyes that pick up that light, that react to the particular energy level that visible light has, and also photosynthesis. Where plants are able to take in sunlight, combine it with carbon dioxide from the air, and produce structure. They basically take those two ingredients and build structure from it. And again, it's all down to the fact that the light has the right amount of energy to interact with the chemicals in the plant. And we would not have oxygen to breathe were it not for that, because the oxygen in our atmosphere has come about it's a byproduct of the plant's photosynthesis. So it's a waste product of basically the oxygen that we breathe. Is something that the plants
It's plant poo.
The plants exhale it. It's a byproduct
Plant
of
excrement. That's what we are living on.
yeah.
But we wouldn't be able to do that if it wasn't for visible light.
Yeah.
But the plants wouldn't have evolved to
Yes.
use it.
Yeah, maybe
But then
if we were getting bombarded with ultraviolet, maybe they would have evolved
to do
yeah
triffids today. The triffids would be giant plants would be our masters.
Yeah. So chances are, like as I mentioned earlier, some insects can see ultraviolet. Chances are there are other animals who experience vision different from how we do because they can see slightly different range of colours or whatever.
Yeah.
So it's, of course we'll never be able to actually ask them that question or ask
No,
them
never say never.
what it's like.
AI implants.
So that's visible. We'll move a little further up the energy spectrum and we'll go for ultraviolet. So now you're talking about a wavelength of between 10 and 400 nanometers, which, to put that in a more understandable but not really understandable figure, is 5 million waves per millimeter.
So the last one we were 2,000, were we? No, the last one
was 2 million waves per millimeter.
So
that
this
was
is
visible
5
light.
million.
This is around 5 million waves per millimeter.
Yeah.
So as I mentioned earlier, it's present in sunlight. Some of it gets blocked by our atmosphere, thankfully. Not all of it, but some of it does. It's got enough energy. So because we're up to a higher frequency here, we are talking about more energetic photons. So the photons now have enough energy to excite electrons strongly. So when that ultraviolet light hits a substance, the electrons in that substance, if depending on what that substance is made of, get affected, excited, we'll call it, by that energy that's in those ultraviolet photons, and it can trigger chemical reactions in that thing that the light has hit, or it can even break molecular bonds. So in other words, break a molecule into its constituent elements. So. Yeah, so that just the incoming energy. If you think about it, it's like a very fast car crash.
Okay, so remember that ad for Harp years ago? It was like kind of Sally O'Brien, was it? And the way she might look at you.
Yeah.
And your man said you could fry an egg on the rocks out here if you had an egg.
Yeah.
So was that infrared or ultraviolet?
Not ultraviolet. No. I mean that would be the infrared element of the sunlight heating up the rock.
Okay, there we go.
Yeah.
That's another mystery solved.
Yeah. No, not ultraviolet. No.
No.
So the ultraviolet might have been weathering the surface of the rock.
Okay.
It might,
yes.
it might have been chemically altering the molecules on the surface of the rock because its energy, its photons had so much energy that they're doing weird things to the electrons on the rock.
Yeah.
So we for our own convenience of classification, we split the ultraviolet into 3 bands. So band A, or UVA, that's the longest wavelength. It penetrates deeper than the other ones, and it causes tanning and aging. But it's actually the aging in terms of making your skin get all wrinkly if you get too much sun exposure and so on. But it's actually the least energetic of the UV. Then we've got UVB. So that's what causes sunburn. So that's actually what damages our skin when we get sunburn. And
so UVA doesn't damage us too much, except make us wrinkly.
So it tans our skin without burning mostly.
Right.
Now, if you get a lot of UVA, you will get burnt by it, but you're more likely to be burnt by the UVB element because it's more energetic. Incidentally, though, it's also responsible for vitamin D synthesis. So they say when you go outdoors in bright light, it helps your body to generate vitamin D. It's
UVB.
It's the UVB hitting your skin, so it's a double-edged sword. It's burning you, but it's also generating the vitamin D.
So we can't get rid of UVB.
No, we
just live with UVA.
Right amount, moderation in all things. But it also can cause DNA damage because the energy of those electrons, when it hits the DNA in your skin cells, it can actually mutate or damage the chemical structure of the DNA. So that's a potential for causing skin cancer.
All right. Okay.
So essentially, your DNA is like your instructions to tell your cells how to grow, when to die, all the rest of it, what shape they should be. Suddenly, the instructions get a bit scrambled, and you get uncontrolled growth.
But you're being very pessimistic, though. Maybe they'd be scrambled into you're going to live forever and be completely healthy.
Oh, perhaps, yeah, and there may be a few people like that living amongst us, but they're very good at hiding. Anyway, and then band C, the most energetic, UVC, definitely dangerous to life. Thankfully, most of it is blocked by our ozone layer in the atmosphere, other than where that hole is down near New Zealand.
Right.
But it's used in like we can create lamps that created artificially, and that's used for germicidal lamps. Have you heard of those? They
No,
kind of for
I think you're just
sterilizing-
making up words now. Germicidal.
So it can be used, for example, in water sterilization. So you can pass, water which has bacteria or viruses in it through a bank of these UVC lamps, and those microorganisms can't cope with that, and it kills them. So
okay.
it's a kind of a form of sterilizing things. Yes, that's ultraviolet, and it has all kinds of other. So there's a lot of ultraviolet coming in from the sunlight, and other bodies that don't have an atmosphere to protect them, like the moon, for example. The ultraviolet hits the surface of the moon and does all kinds of interesting things to the moon dust on the surface of the moon and other planets that don't have an atmosphere as well. So we're lucky we have that atmosphere there to protect us. Even higher energy, of course, is something that most people are familiar with: X-rays, because of hospital diagnosis.
Yeah, and those X-ray specs you used to get as a kid.
Yeah,
You used to be able to see through people's clothes, allegedly.
Yeah, allegedly. And if there were true X-ray specs, you'd actually see through the people as well. Except
Well, maybe they were just calibrated successfully.
There might have been UV specs.
Yeah.
It's slightly lower energy. But in terms of wavelength, we're talking about from 0.01 of a nanometer up to about 10 nanometers.
Which in English is?
Which in English is about 1 billion waves per millimeter.
Okay, that's not, it's in English, but I still don't understand.
So that's 1,000 million waves per millimeter. I mean, these numbers are just bonkers, and you can't, on a human scale, you can't visualize them. So how are they created? Well, one way is if you have high energy electrons. So, some heavy elements, like heavy metals, like lead or whatever, they have electrons at multiple different circuits, like orbits around the nucleus of the atom, and the inner ones would be fairly high energy. So if you get some of those, I just use lead as an example. There's other kinds of high energy electrons as well. But if they suddenly stop, like for example hitting a piece of dense metal, that sudden change in speed.
So when
and
the X-ray hits the metal.
No, we're talking about how the X-ray gets produced.
Okay.
So a sudden stop of a high energy electron would be sharp enough to generate a photon of X-ray radiation.
Right.
So you're talking
you're
about
talking about not shaking a lead.
No. You're talking about maybe a thing like an electron beam gun, like what used to be in the old-fashioned TVs. Remember the old big televisions?
Oh, the fluorescent tube thing out the back. Thing.
Like firing a stream of electrons from that at a plate of lead, for example, might be enough.
Not going to do it in the kitchen.
No. But that's just one example. So it's like it needs a lot of energy in the source material to actually generate X-rays, because they themselves have so much energy.
In nature, though, they're created by stars and stuff, is it?
Yeah, energetic events in space, we'll call them. So could be stars, could be collisions, could be matter orbiting around black holes at high speed, that kind of stuff.
Right.
The photons have so much energy that they can knock electrons completely out of their orbits, away from their parent atoms.
Subatomic pool.
That's called ionization. Yeah, subatomic pool, good one. Yeah. Or snooker, if you get it in the right order. But yeah, they so they can ionize other things that they hit, because they've got so much energy that in other words, kick an atom out that shouldn't be kicked out. So why can X-rays show us bones but not show us flesh, which is what they're used for diagnostic purposes? So it's all about the density of the tissue that they're passing through. So softer tissue, like your muscles, your blood vessels, there's fairly large gaps between the electrons, and the X-rays are able to pass through mostly. So there'd be few, if some of them get stopped, but not many. But then you come to something much denser, like the calcium in your bones, or if you have a pin in an old fracture in your leg, the metal in the pin, that kind of thing. Much smaller gaps between the electrons, and they stop the X-rays from getting through. So you've got a source of X-rays shining on your leg from one side, And on the other side, you've got a photographic plate which those X-rays are landing on, and the ones that don't get through your bones make an image on the plate. That's kind of how it works. But yeah, it's also used obviously for airport security scanners, materials analysis. They use it for analyzing crystals and so on. Again, it can damage DNA, so using X-rays for diagnostics in hospitals has to be done. You can't expose people to a lot of X-rays.
There's a limit.
There's a limit to what you can reasonably expose people to, and even it's not a hard and fast exact science. So you can have people who have like a very few X-rays that still unfortunately might end up getting cancer from them. It's just it's a risk benefit kind of thing. So there's also X-ray astronomy. We spoke about infrared astronomy, but there's also telescopes that can see in the X-ray band, and they can examine some of the most violent things that are happening, like superheated gas swirling around black holes, neutron stars, which are a very energetic remnant of large stars after they die, supernova remnants, that kind of thing. And you're talking about, these are bodies that have like temperatures in the millions of degrees, and the matter that's that the objects, those objects are so hot, the atoms in them, the molecules in them, are very, very energetic events out in space.
But are there satellites that are just X-ray detectors, or is there are there satellites like, today we're looking at infrared, and let's switch over and see what's happening on?
Well, it would be different. It would
X-ray?
be different equipment. So I mean, it's possible to build a telescope that has different kind of detectors, and you switch this one on or you switch that one on. Specifically, which ones have combined detectors, I don't know. I can't answer that question. But you definitely need different equipment for the different bands of radiation.
And could you detect? Could you use sort of ground-based telescopes for X-rays?
You probably could, because I doubt very much that the clouds in the atmosphere would stop them, or that the atmosphere would stop them.
Yeah.
You probably could, yeah. Finally, we come to the absolute monsters of the electromagnetic spectrum. I said electromagnetic spectrum.
Yeah, there you go. Finally, I knew you'd run out.
Gamma rays. So
Dr. David Banner. I just have to say it every time I see gamma rays.
Gamma rays. Oh yeah, the Incredible Hulk.
Yeah.
Well, he's a lucky man, because gamma rays would usually do more than turn the rest of his screen. So wavelength less than 0.01 of a nanometer. So we're talking about the wavelength smaller than the nucleus of an atom, like really tiny. About 100 billion waves per millimeter. So that's a lot of energy in every millimeter.
Yeah.
So do you remember we said that essentially the photons that EM radiation are made from are pure packets of energy. They have no mass, they're just all energy. So these are, like, gamma radiation photons are probably the single most energetic objects in the universe. Each individual photon.
They're busy little fellas.
Yeah, they like, nuclear reactions are I suppose the primary source that we can observe. So they're produced by radioactive, uranium, plutonium, etc. Fusion or fission. Fusion is what's going on inside in the sun. Fission is what we do in our nuclear reactors, and we're trying to figure out how to do fusion so that we can benefit from lots of free energy.
But there's not actual gamma radiation coming off uranium. It has to be reacted with something.
Oh no! I mean, uranium and plutonium, they are producing some gamma radiation. It's one component.
Yeah.
There are two other kinds of radiation involved in nuclear radiation, which are not on the EM spectrum. They're completely different.
Okay.
But
let's not go there.
But gamma is one of the components of nuclear radiation. So if you have a sufficiently pure sample of uranium or plutonium, there's a hell of a lot of gamma radiation coming from it in addition to the other two. So,
I don't know whether I saw this in a movie or something, but apparently the Aboriginal word for uranium means that which should be left in the ground.
Under a mountain.
Yeah, far away.
Yeah. So, and it's partly, just to digress slightly, the fact that there's Ukrainian.
Ukrainium.
I've just invented a new element. Uranium.
Donald Trump was bidden for it.
The fact that there's uranium in the magma that's, the lava that's in the center of the Earth is part of the reason why the center of the Earth has stayed so warm, because the energy just from that radioactive decay is helping to keep the lava hot.
Okay.
So yeah, what's it used for, gamma rays? Obviously, we need to be very careful about protecting people from that radiation. I mean, it's lethal. You only need a very small amount of gamma radiation to hit you, and it'll kill you or give you cancer. But it is used for, of course, radiotherapy for cancer, where it precisely targets tumors and is given in very measured doses to try and avoid damaging the tissue around. It's used for sterilizing medical equipment, because nothing can survive a decent blast of gamma rays, so the bacteria are definitely going to be killed by it.
Is this are these things coming out of a nuclear explosion? If someone set off a nuclear bomb, you'd have gamma rays.
You would have, that's part of the
damage.
radiation, But I mean, the physical force of the explosion is going to do the primary damage.
Yeah.
I mean, it's the people who don't get killed by the explosion or burnt by the heat blast from it that are going to suffer from radiation poisoning. So we'll just talk about probably one of nature's most incredible spectacles, and that's something known as a gamma.
That's you on a bicycle. Have you seen sending on a bicycle, just cycling along? It's a sight to behold.
Yeah, I mean, I'm trying to go on a straight line. I'm nearly there now. I'm nearly there.
We'll take the training wheels off soon.
Well, yeah, and the guy that walks in front of me with the flag, I won't need him much longer. So gamma ray bursts, they are the most powerful explosions in the universe that we know about. And they're things like massive stars collapsing into black holes or neutron stars merging with each other. These are the kinds of explosions in space that produce them. A gamma ray burst releases more energy in a few seconds than our sun will release in its entire 10 billion lifetime. Like, it's mind-boggling amounts of energy. There's no way you can picture that in our poor little monkey brains. But
I can.
It's basically Einstein's E is equal to mc squared in action. So that's matter and energy. So matter literally converted directly to gamma ray energy because of it was annihilated during a very forceful event. They're so powerful that if one happened within 5,000 light years of Earth, now remember the sun is 8 light minutes from Earth, so 5,000 light years is a long, long way away. There's a lot of other stars closer to us than that. If one happened closer than 5,000 light years from Earth, it would probably kill everything alive on the surface of the Earth.
But not for 5,000 years.
No, well, I said closer than 5,000 light years.
Okay, well, say it was 4,500 light years, But
yeah.
But in the future, this could be happening. This could be barreling towards us right now.
Yeah, because nothing travels faster than the speed of light, which is the speed the gamma radiation will be traveling at. So we won't see this explosion happening before the gamma rays hit us.
Yeah.
So,
So we might as well just live as if there's a giant gamma tidal wave hurtling towards us.
Yeah, let's party like it's 1999. Now, look, where do you go after that? I mean, follow that, gamma ray bursts.
Well, gamma ray bursts are, but I mean, is that it though? Is that the upper limit? Is that as far as we know?
That's as far as we know, yeah. That's as far as we know,
But is it possible that there's like gamma plus or like lambda or wherever you would go after gamma?
We're kind of, not only are we reaching the limit of our knowledge, we're reaching the limit of my knowledge of mathematics too. So... I
apologise, listeners. We should have found this out. Okay, we're gonna say that gamma rays are the daddies.
That's what we know of at the moment. Yeah.
Yeah.
But it's the EM spectrum. It's something else. The amount of variety that one substance is not even a substance. That one phenomenon, we'll call it. Everything from radio waves that are kilometers long down to these gamma ray bursts that are like minuscule.
And of course, the probably the lines in between all of these different categories are pretty arbitrary.
Oh yeah, I mean, these different bands we've been talking about, gamma rays, X-rays, ultraviolet, blah, 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 they're all human divisions.
Yeah.
I mean, there isn't like a sharp change when you hit the border, as it were.
Yes.
I mean, so something that's slightly on the gamma ray side versus slightly on the X-ray side, very little difference between them.
Well, you want your radiologist to know. What did you say? Did you say gamma ray? No, X-ray. It's definitely an X-ray.
Yep.
Well, look, that was a hell of a tour around the electromagnetic spectrum.
Yeah.
Quite a comprehensive one.
Yeah. We filled an hour. I can't believe we filled an hour. When I looked at all the notes we had made, I said we'll be lucky to get to half an hour. So it's funny the way time just drags on. Do you know,
It doesn't drag on. It doesn't drag on.
because
Flew
we're
along.
traveling too fast. I bet you that's it. We've accelerated.
We've
towards the speed of
accelerated it
light.
so time seems slower. So if you actually speed up this podcast, time will go slower for you. So slow it down and time will go faster. There you go.
My brain hurts.
I know, mine too. I think we'll leave it there. That's enough with the science for this week. I'm Joe.
And I am Senan, and we'll see you all again next week, where we will not be talking about the EM spectrum.